Hello, I'm Martha Nance again. I'm the director of the Huntington's Disease Center of Excellence at Hennepin HealthCare in Minneapolis, Minnesota, and I just want to get our day started off. The title of this talk is Letting the Genie Out of the Bottle. So first of all, I want to acknowledge, does anybody raise your hand if you think that 2020 was kind of a dark, gray, gloomy year between COVID and elections and global warming and George Floyd and this and that and the other? Raise your hand again if you think that 2021 was maybe even a little bit darker or gloomier. Again, COVID keeps going, and I think probably by now everybody knows somebody who was really sick with COVID or maybe even died from COVID. In the Huntington's community in March, we had the disappointing news from two clinical trials that were much awaited and with great excitement. Is there any reason to think that there's any light to be seen, any bright lights either now or in the future? I think I know of a few people who've gotten married during COVID or had a baby, or somebody who had a gentle, pleasant, quiet death. I think we have started to see some little bits of light. Maybe families have been brought closer together. And I really want to focus a little bit on that as we get to the end of the presentation. One thing to be happy about is the number 22. Actually, I think it's 23 now. 23 is the number of people that will be speaking to you over the next 4 hours. It's pretty scary if a bright light in your year is coming to a Huntington's disease conference, but I have to say that a bright light in my year has been planning this conference. The commitment and enthusiasm of the 22, or maybe it's 23 or even 24 by now, speakers that you'll hear from, it's really been a pleasure to work with them and to put together this presentation. Really outstanding clinicians, outstanding researchers that you'll hear from today. So I hope you enjoy that. But what I really want to get to is kind of the science of this talk. I want to sort of get you started, kind of up to speed, make sure everybody's kind of on the same has the same grounding as we talk more about science later in the conference. And what I've been saying for the last couple of years is the genie is out of the bottle. Well, what do I mean by that? Huntington's disease is special. It is always caused by a particular mutation called a CAG repeat expansion at a particular spot in a particular gene. And you just can't say that for Parkinson's disease or Alzheimer's disease, some of these other neurodegenerative diseases. Because it is always caused by a particular genetic mutation, we have the ability to identify accurately who will develop Huntington's disease even long before they have symptoms. Now, whether you should do that or not is another discussion, at least in the clinic, but in the research world, it's really helpful to be able to tell ahead of time who's going to develop the symptoms so you can start to tease apart what are the very earliest changes that take place even before the disease is overtly recognizable by family or physicians. So this allows us to dream of treatments really directed at that root cause of Huntington's disease, the gene mutation, that could potentially be delivered as soon as or even before any damage is done to the cells in the brain. We're not there yet, but that's when I say the genie is out of the bottle. Research approaches to developing these kind of treatments are well underway and are not going to go away. So what might be some ways that you would address or treat the genetic abnormality that causes Huntington's disease? And I'll talk a little bit about these in a minute. I want to focus right now on bullet point number 2, turning off the abnormal gene. And there are different, you might call them drugs or different constructs, different approaches that have these funny names, ways to try and turn off the gene. One is called antisense oligonucleotide, or ASO. Another one is RNA interference, or RNAi. And there are a couple versions of that, microRNAs and small interfering RNAs. And then ZFP stands for zinc finger protein. So these, whenever you read these words, if somebody's developing a treatment like this, they're working on strategies to kind of turn off the abnormal gene. Well, what in the heck do I mean by turn off the abnormal gene? So this is your science slide. So in your body, you have many cells. Inside the cell is a nucleus, and there's another structure inside the cell called the ribosome. You could erase those words and think of that as being your house, and the nucleus is basically the library where you keep books and encyclopedias, and the ribosome is the kitchen. So now we see the genes are the recipes that tell your cell how to make chemicals that you need. Those genes are stored in the nucleus. This is a picture of the normal Huntington gene in red and the abnormal Huntington gene in blue. The abnormal gene has too many CAG repeats, so it's bigger than the normal gene. If you want to use that recipe to make a protein, the problem is you have to do the cooking in the kitchen. That happens in the ribosome, but you can't take the encyclopedia out of the library. So how do you get the recipe to the kitchen where it needs to be? Well, you make a Xerox copy. And the Xerox copy is called mRNA. And there's a copy of each of those genes, and you want that Xerox copy to go to the kitchen, to the ribosome, where it's used to make the protein. So that's the happy situation where the normal gene made a normal mRNA that went to the ribosome and encoded a normal looking Huntington protein. The idea with the ASOs, or the interfering RNAs, is that you put something into the cell that recognizes and sticks to the abnormal RNA. And once you have two pieces of RNA stuck together, that's recognized as not being right and gets broken down. And so that abnormal RNA never gets to the kitchen. So then, hey, you only make the normal Huntington protein. Shouldn't that be a fix for Huntington's disease? That's what we've been very excited about. But the disappointment that came along in March this year was the reports from two trials where it just didn't work out. So the first trial was sponsored by a company called Roche. This was a very large trial, 800 patients involved in the trial, what we call a phase 3 trial, divided into 3 groups. There were placebo, there were people who got the drug every other month, and people who got the drug every 4th month. And this was delivered by a spinal infusion. So these participants were getting spinal taps every other month scheduled for 2 years. And what we think that this drug does is to reduce the production of the Huntington protein. An important comment is that this product turns off both the normal gene and the abnormal gene. So in theory, you reduce all of the Huntington protein that's being made. And maybe that's important to keep in mind when we ask ourselves what went wrong. It turned out that the people on the 2-month drug had worse scores on the, quote, composite unified Huntington's disease rating scale, which is sort of how we were measuring how the people were doing. The people getting the study drug had worse scores than people getting the placebo at a point in the study where more than half of the subjects had been in the trial for over half of the planned course of the trial. And this was statistically significant. So you could guess that it wasn't just a little blip. And if you just kept going, everything would wash out in the end. More than half the subjects were more than half the way through the study. And so the safety committee that gets to peek at the data recommended to the company that they discontinue administering the drug. But importantly, the idea was also to continue to follow those subjects until the study was planned to be over, just not keep giving them the study drug. And that would allow the researchers to sort out if the people getting the real drug got worse. Well, what happens if you quit giving them the drug? Do they continue to get more worse than the patients on the placebo, or do they stabilize, or do they actually get better again? That part of the trial is still in the works, and we really don't have any more data about it. You will be hearing later today from the leaders of the Roche trial, who will be happy to answer questions, more specific questions that you have about that. So this was almost kind of like this drug was too strong. The next study that came out was a different company called Wave that was just doing a small trial, small number of patients, just to try to find the optimal dose. And they had actually come up with two different drugs. Their drugs were specifically designed to affect just the abnormal Huntington protein and not mess with the normal gene, the normal RNA, the normal protein. This study was scheduled to end in March, and it did. And they found that there were no major complications from the treatment, but the problem was that they were unable to show that their drug actually lowered the level of the Huntington protein. So it's kind of like this drug wasn't strong enough. So now you've got the Roche drug that's too strong. You have the Wave drug that's not strong enough. Wave is planning to look at a third compound starting later this year or maybe early next year. So we had the disappointing news of these two trials that just didn't work out the way we had hoped. So how do you move forward? Number one, we all owe a great thanks, a great debt of gratitude to the pioneers who participated in those trials, the patients, their families, the researchers, everybody keeping this going through the difficulties of the COVID pandemic. So, bless you, thank you to those participants. We learned from these experiences. I was struck that this was the same month in March that Elon Musk and SpaceX blew up two rockets. And guess what? Later this year, he had people flying out into space. So you learn from your experiences, you move forward with the next study and the next one. And if one's too strong and one's not strong enough, you try and find something in the middle. So in some ways, the failure of these two trials empowered many other companies, many other sponsors to move forward more rapidly and be more excited about the products that they're developing. So the bullet point number 2 is the one I've talked about, where you turn off the abnormal gene. There are probably 10 different companies now working on products that are similar, have a similar effect, but may be administered in a different way or may have slightly different characteristics that make them maybe more favorable in some ways. Unicure is the other one that's currently in a clinical trial. That product is actually administered by a surgical injection directly into the brain, for better or for worse. What are some other strategies to address the genetic abnormality that causes Huntington's? You'll hear about some of this later on. I think that Matt Bauer may talk about, at least briefly, about bullet point number 4. This is sort of the newest news that we think. We've always thought that if you had a blood test and you find out that you have 44 CAG repeats in one copy of your gene, that you will forevermore have 44 CAG repeats in the gene in your body cells. But we now know that at least in the brain cells, as the years go by, that repeat number may actually get bigger. And that it may be the increase in the repeat number that corresponds with when the disease really gets started. So if you could prevent further increases in the CAG repeat expansion region of the Huntington gene, you did not wake up this morning thinking you would understand what those words mean. But if we can prevent further increases in the CAG expansion region, that might delay or who knows, maybe prevent the onset of Huntington's disease. There are several companies looking at treatments that might have that effect. If you tell any 8-year-old child about the gene thing and that people have a normal gene and a not normal gene, and then ask the 8-year-old, can you think of any strategy to address Huntington's disease? They will universally say, can't you cut out that abnormal gene? And for years I've said, well, great idea, but the gene is in all the cells in your brain, and how can we ever get scissors small enough to actually cut out that abnormal gene? When you hear about or read about CRISPR, CRISPR is basically little tiny scissors that can get into the cell and cut out that abnormal gene. The challenge with CRISPR is to get those little scissors to behave and only cut out the gene that you want them to cut out, and not actually snip or cut other genes, and to deliver that to the cells of interest in the brain. CRISPR is currently in the laboratory as relates to Huntington's disease. It is not in clinical trials yet. And then another thought, remember we have that the gene that's in the library. You've got to make the proteins in the kitchen, and you have that RNA that travels between. And that RNA is basically a copy of the recipe. And ladies listening to this may relate better to this than the guys, but every so often I read Ladies' Home Journal, and there's a recipe that starts on page 10, and then it says continued on page 83. And there's 70 pages of advertising and other articles in between the first 2/3 of the recipe and the last third of the recipe. And if I want to cut out that recipe and put it in my recipe notebook, I have to cut out the part on page 10, and then I have to get through 70 pages of junk and then get to the other third of the recipe. And then I cut that out, and then I put them together. Well, believe it or not, the same thing happens inside the genes in your cells. Part of the gene is here, and then there's sort of, they used to call it junk DNA, or you might as well just call it advertising. And then the next section of that recipe, and then another little bit of advertising, and then the third section of that recipe. And so when you make that RNA, you first have that all that stuff with all the advertising stuff in between. You have to splice that out. You have to cut that out and put the two parts of the recipe together. And that's called mRNA splicing. Well, in the case of Huntington's disease, what you would like to do is interfere with the appropriate splicing of the abnormal mRNA so that it doesn't get spliced properly, so that then that recipe can't be used. It goes to the kitchen still with the 70 pages of advertising, and then you just kind of get lost in the shuffle. So believe it or not, this strategy has worked for other neurologic diseases, particularly some muscle diseases. And so there are several companies working quickly to develop treatments that are mRNA splicing modulators that might be relevant in Huntington's disease. And probably the company that has the lead in that at the moment is a company called Novartis. So expect that you may be hearing of trials for drugs that are RNA splicing modulators, and those are the ones where you're just cutting out all that advertising in between the sections of the gene. So one other thing I want to talk about briefly is, and this is a completely different thought, but again, to me, it's a hint of how we're going to be thinking about Huntington's disease in the future. Back in 1981, one of my mentors, Ira Scholson, along with one of his mentors, Stan Fahn, developed a staging system for Huntington's disease that is now lovingly known as the Scholson-Fahn total functional capacity scale, or sort of a rating scale for people with Huntington's disease. You may have used this, your doctor may use it. People say, what stage are you in? Well, I'm stage 2, I'm stage 4. This staging scale begins with the diagnosis of Huntington's disease and the recognition of functional disability or functional disturbance. So that was kind of the state of the art as of 1981. Well, then in 1993, we found the Huntington gene. We had to add a new sort of stage to this. So there's having symptoms of Huntington's and being stage 1, 2, 3, 4, or 5. And then there's knowing that you have the gene, but not being diagnosable yet, what we would call presymptomatic. And how can we get even more refined in our understanding of the course of Huntington's disease? Well, For many years, many of you, or perhaps your relatives or your parents before you, have participated in studies like Predict HD, Track HD in Europe, Enroll HD. These studies collectively have collected years of data from thousands of people with Huntington's disease, at risk, not at risk, including MRI scans and spinal fluid measurements. You'll hear about the spinal fluid measurements later today from Ed Wild. And from these, we can now start to develop what we call biomarkers, other ways of measuring the progression of Huntington's disease besides just going to the doctor and having the doctor say, well, this looks like 1+ chorea, or this looks like 2+ chorea. How can we have more sensitive measures that may even be changing earlier in the course of the disease before the person has obvious diagnosable Huntington's disease? So a committee was set up. I'm not on the committee, but it's led by Sarah Tabrizi in London to review the results of all these studies and to decide which biomarkers have enough science behind them to be used in a clinical trial. It's probably going to be brain MR imaging, not just the MRI scan that you go to the local doctor and the local radiologist kind of says, yeah, it looks okay, or I see a funny spot. This is really research level measurements of three-dimensional measurements of the structures in the brain. And another set of biomarkers that probably will be used in the future would be some of the chemicals that we can measure in the spinal fluid. Maybe don't have quite as much data about those yet. So now we have a new course of Huntington's where you've still got the stage 1, 2, 3, 4, 5, the Schultz and Fahn staging for people who are symptomatic. But then we have people who are gene positive but completely normal in any way that you could possibly want to measure. You've got people who are gene positive whose MRI scan is just showing slight changes in the size of the caudate nucleus, but yet they have no findings on their exam, no clinical features. And then you may have patients who are gene positive, maybe the caudate nucleus is a little smaller, and they also have just a subtle finding on a research exam. One of the tests we often use is a thing called the symbol digit modality test, or SDMT. And sometimes the performance on that test may start to change, even at a time when a person is not having any trouble balancing their checkbook or going to work. It's just a very slight change and no functional change. So now we've got more stages. And if we can identify a biomarker that reliably distinguishes gene carriers from non-carriers, even before the person has clinical or functional symptoms, and you can see that biomarker changes over time. So in the little graphic here, the normal range is that yellow strip. And the person with Huntington's disease starts out in the normal range, but now you can start to see changes even a number of years before the person is diagnosable. Then you could maybe use that biomarker in a disease-modifying trial to evaluate the effects of the treatment. And that might empower people who are not even yet diagnosed with Huntington's disease to potentially participate in some future trial of a disease-modifying treatment. Again, this is all in the future, and importantly, we're talking about research. We're not talking about changing the clinical definition of Huntington's. We got to walk a very delicate tightrope here. We're talking about research level MRI scans. Maybe we'll eventually get to where we're using spinal fluid tests to determine whether cells in the brain are starting to be damaged or not. Still in today's clinic, the neurologic exam, formal cognitive testing, those are the tools to tell if somebody has enough findings to be diagnosed with Huntington's disease. And you're not disabled from work due to Huntington's disease until the Huntington's is getting in the way of working. It's not like the MRI scan done 10 years earlier means that you are diagnosable with Huntington's or need to go on disability at that point. This is a research thing we're talking about. Now, obviously, if we develop a disease-modifying treatment, then we would use some of these tests to determine when do you start that disease-modifying treatment. So really, I think, exciting ideas for the future, multiple different companies working on multiple different approaches to really get at the root cause of Huntington's disease. Importantly, you'll hear from some of these folks later on today. Importantly, though, we as a research community are not neglecting the fact that no one treatment may be the miracle cure that we all dream of. There are other approaches, both to treating the disease and to treating symptoms in Huntington's disease, which you will also hear about from some of the lead investigators later today. So, the Genie is out of the bottle. With the Genie comes your 3 wishes. And I think you could say, I wish for a cure for Huntington's disease. I think short of that, that's kind of like wishing for world peace. It'd be great. Maybe we'll get there. But my 3 wishes would be to have researchers like the ones you're going to hear from today. These people are consummate researchers. I call out in particular Jim Gusella, who was on the team that first localized the Huntington's disease gene back in the early 1980s. It's now 2021, and Jim Gusella is still working on Huntington's disease. This guy has spent his entire career trying to find better answers to this disease. And clinicians like Jamie Hetch-Martin, Andrew Duker, Matt Bauer, Danny Vega, some of these folks that you'll hear from today. And by the way, many of these researchers, Andy Fagan, G. Bang, Michael Hayden, Ralph Ryman, Dan Clausen, Aaron Furst-Stimming, these are also consummate clinicians. And Victor, Sam, Danny, Catherine, these folks are all leading researchers in the clinical research world. So we are fortunate in the Huntington's community to have a group of clinician researchers who really get it, that there are patients and families anxiously waiting for answers. As patients always say, work harder. And I think the clinicians in the group really advocate on behalf of the patients and families to move quicker and to do treatments that really do make a difference. And the biggest wish is for HD patients and families like you. I was just blown away by the 800 enrollees in the Roche trial in less than a year, keeping it going through COVID. What an amazing commitment from the Huntington's community, patients, families, researchers, to keep this going. We cannot get better answers for Huntington's disease without the support of patients and families. You can't get better solutions to Huntington's without the work of the researchers. And nothing's going to happen if you're not getting adequate care, timely diagnosis, adequate treatments, good support for your families from the clinicians. So I hope you enjoy the rest of the day. I think it's going to be an amazing day if you actually stick it through to the end. There's a lot of information and a lot of support to be had. So thank you for listening and have a great day.